This chapter contains more op-amp circuits in negative feedback with a few variations. Here we have an op-amp circuit in inverting configuration. First, we calculate the gain and then immediately convert the gain to decibels. If FU is 1 megahertz for this op-amp, then we can find the high frequency roll-off by taking FU and dividing it by the gain, in this case equals 20 kilohertz. The low frequency roll-off is determined by the capacitors, but in this case we have one capacitor on the input side and one capacitor on the output side. Because of the two capacitors, we need to use our formula for the low frequency roll-off twice, that is, F equals 1 over 2 pi RC. It looks like the low frequency operation is limited by the input capacitors, and we can only go as low as 106 Hertz. We now have enough information to compute our Bode plot as shown on the diagram. Our Bode plot shows that the maximum gain is 34 decibels, but at the two corner frequencies, the gain will drop down by 3 decibels to 31 decibels. A differential amplifier is used to amplify signals from very small sources, such as a microphone or from a sensor. The differential amplifier is still in the inverting configuration, and the formula is the same, in this case R2 divided by R1. Because the differential amplifier uses both inputs, that means that both inputs will be receiving the same amount of noise, and the noise could be greater than the signal we're trying to amplify. The noise going into both inputs will be amplified equally, and this is called common mode gain. Common mode gain is calculated with the formula shown, and when we convert it to decibels, we get negative 48 dB, which is a very low gain. A gain of negative 48 decibels means that the op-amp is rejecting the noise. How well the op-amp rejects noise is called common mode rejection ratio. The rejection ratio is calculated by taking the gain and dividing it by the common mode gain. A common mode rejection ratio of 74 decibels means that the op-amp has rejected a huge amount of noise. Often, an op-amp has to drive a heavy load such as a motor or a speaker. But an op-amp can only put out a very low current, and this is called maximum short circuit current. In this case, it's only 25 milliamps. In the current booster circuit, the output from the op-amp feeds the base of the transistor, and it is the transistor that supplies heavy current to the load. If the beta of the transistor is 100, then the maximum current that we can put out is 100 times 25 milliamps, in this case 2.5 amps. Notice that we always calculate the gain, but in this case we ignore the gain and it's just concentrated on the current that's to be delivered to the load.